This is Unit 5, Lesson 3, Part 1. So we're going to be looking at zeros, what those are, how we find them, so zeros of these polynomial functions. So quick definition, a zero is a point at which the function intersects the x-axis. So they are also known as x-intercepts. We've definitely referred to them that way before when we looked at lines or looked at parabolas. So x-intercepts is a synonym for zeros. A polynomial function of degree n can have at most n real zeros. So if it's a quadratic, if it's an x squared, it could have at most 2 zeros. We say at most because it might have 1, it might have 0. So a cubic could have up to 3, a quartic could have up to 4, etc. An even degree polynomial has an even number of zeros. Or it might have no zeros because we kind of consider 0 to be like the first even number. An odd degree polynomial has an odd number of zeros. So these rules have like sort of an asterisk next to it, which we will get to at the end of the notes. All right. So we're going to identify our zeros by graphing. So graphing each function means we are going to use the assistance of Desmos to graph these for us. So I'm going to plug this equation in. You can follow along if you want to pull that up on the side. So x to the third plus x squared minus 2x. So this is what our graph looks like. I can show this to you here. So remember, in our last couple lessons, we've been using Desmos and showing you how you can click on it and then look at all of these important points right here. So we've got this point, oops, come back. This point right here is negative 2, 0. So you can plot that. This point up here, it's kind of a weird decimal, but a little bit past negative 1 and a little bit above 2. It's kind of like right in that corner. Right here at the origin. This one down here. Again, kind of like right in the middle of that first grid right there. And this one right at 1, 0. So we've got a bunch of points right here, and then we just connect the dots. That gives us plenty of information to see the shape of the graph. So we graph it, and then the directions say identify the zeros. All right, so the zeros are, remember, the points at which the function intersects the x-axis. So we want to write those just as x values. So we're going to write x equals, and you can see there are 3 of them, 1, 2, 3 points where we intersect the x-axis. So we're going to write it in our set notation. First one here is at negative 2 on the x-axis. The next one is right at the origin, so that is x equals 0. And then the third one is just at 1 right there. So those are our 3 different x-intercepts. What that means is that these are solutions to this equation right here. If I were to take any of these 3 numbers and plug it into this equation, I would get 0. That's why we call them zeros. Anything else if you plug in will not give you 0. Let's try the next one. We got a nice long function to plug in here to Desmos. So I'm going to type this in. Type carefully. Make sure you've got all your negative signs and everything. So plus 4x to the third minus 2x squared minus 4x plus 3. So crazy function here. So I'm going to zoom a little bit so we can get these points. So click on it. We've got x-intercepts highlighted. There's a y-intercept. We've got our maximum points highlighted. So this, we've got a point at negative 1, 0. So that is right here. Let's see if I can get these both on the screen. Up here, so it's almost at negative 1/2 and then up at 4. So that is right here. Right here is 3 on the y-axis. Down here it hits at 1. Up here we've got another high point, so basically 2.5 and then up at 4. So here's 2, 2.5, up at 4. And right here that's 3 on the x-axis, so 1, 2, 3. So you've got these points. Looks a little crazy just looking at the points, but you can see from Desmos that it makes this sort of M curve here. So just follow along, connect the dots, and our graph looks like that. So our goal here was to identify the zeros, so we're going to do just like we did here. X equals, little squiggly brackets, so we're going to run down the x-axis, identify any place where it hits. So this point right here was at x equals negative 1. Comma, and then this one was at positive 1, Now this is something that we're going to talk about on the next page. See the way that this bounced rather than crossing? It technically counts as 2 answers. It's like a double repeat answer because it bounced instead of crossing. And then this point right here is 3. So you can see this kind of gets messed up on this rule that we wrote up here because this is an even degree. It's a degree of 4, but we only have 3 answers, 1, 2, 3. This is why I said this kind of has an asterisk on this rule right here because this one, the middle one, we technically count that as a double because it bounces instead of crossing. Like I said, I'm going to give you some specific rules for that on the next page. So those are our first couple. Next, we're going to talk about linear factors. Linear factors are what happen when you factor down the equation. So if we look at this one right here, we want to write it in its factored form. So I am going to take this expression, factor it down as much as I can. You remember from earlier in this chapter, the very first thing we try to factor is a GCF. So you can see 1, 2, 3, all of those terms have an x. So I'm going to start by factoring out an x as a GCF and then put the leftovers in parentheses. So without the x, this is an x squared minus, and then this is just a 2x minus, and then just a 15. So that's the first step of my factoring. And then hopefully you can tell that this middle part can factor more. So here's the x. And then this is just a classic trinomial, so it factors down into 2 pieces. It starts with x times x, and hopefully we've had enough factoring practice that these are relatively easy by now. These numbers are supposed to multiply to negative 15, and they're supposed to combine to a negative 2. So that would be a negative 5 and a positive 3. So those are our factors. And then when we set these equal to 0, because remember, like we said up here, the technical reason we call these zeros is because they make this expression equal 0. So if I were to accept this expression equal to 0, I would get 3 different answers. I would get x equals, if I set this equal to 0, it's just 0. If I set this equal to 0, I get a positive 5. And if I set this equal to 0, I get a negative 3. So that's one thing I can do is I can look at what we call linear factors by factoring this down. So I don't need Desmos, I don't need the graph, I can just set up by factoring. All right, so we've got some definitions on the next page. This is what I was talking about with the double x-intercept. So this is something called multiplicity. So the definition here, it's equal to the number of times its corresponding linear factor occurs, which sounds like a really crazy sentence. I'm going to factor down this expression and then explain what exactly that definition means. So we're going to do another one, this factoring version like we did on number 3. So this, just like number 3, we have a GCF of x that I can take out. So take out the x, that leaves me with x squared minus 6x plus just a 9. And then this part, just like number 3, can factor down a little bit further. Oops, there we go. So this, kind of traditional factoring, I start with x times x, that gives me my x squared, and then the missing pieces are supposed to multiply to positive 9 and add to negative 3. I'm sorry, add to negative 6, I was getting ahead of myself. So it would be negative 3, negative 3 right here. So sorry, to repeat, multiplying to 9, adding to negative 6. So this is a repeat factor. So when we say equal to the number of times its corresponding linear factor occurs, this factor occurs twice. So when we write down our zeros, this one, if I set it equal to 0, I get 0. And then this factor only appears once. Okay, so we consider its multiplicity, I'm going to abbreviate, its multiplicity is just 1. It only appears one time. And then our other answer, if I set this equal to 0, I get 3. If I set this equal to 0, I get 3. So that's a repeat, and that's what this definition means. So I get x equals 3, and because that factor occurs 2 times, I consider that to be a multiplicity of 2. So technically, I have 3 answers, which should make sense because my degree is 3, I have 3 answers, but I only have 2 unique answers because this guy technically counts as a double. So if you're looking at the graphs, like I said on the previous page, this one would cross right through, this one would actually bounce. And that's what we're going to look at with this next example. So these factors right here, we're going to graph it. We know what it looks like in its factored form, so we are going to graph it on Desmos and kind of compare the factored form. So here's our old equation. There we go. So we have x to the third minus 6x squared plus 9x. Okay, so here's our graph. So we're going to click on it so we can get our important points. So first important point is right through the origin. So I'm going to get both of these on the screen. So right through the origin. Then it has a local or a relative maximum at 1, 4. So over to 1, up to 4. Right here it has an x-intercept at 3, 0. So 1, 2, 3. And then that's it. So like 3 important points. Make sure you know what the shape looks like. So you're kind of mimicking what you see on your screen. It goes up and then it bounces right here and then goes back up after that. So there is a difference between a cross and a bounce. Okay, if the multiplicity is odd, so this one, 0, had a multiplicity of 1. If the multiplicity is 1, it's going to cross right through at that x-intercept. So we say the graph crosses at that 0. If the multiplicity is even, so x equals 3, because these are the same equation, x equals 3, the multiplicity was 2. You can see what it does there. It taps the graph and then goes back in the other direction. So we consider that to be a bounce. So the graph either crosses or bounces, and it all depends on what the multiplicity is. And you could see that on the previous page with the one that bounced. That means it must have a multiplicity of 2. All right, so our last set of examples that we're going to look at, this one's in its factored form. So we're going to write down what the 0 would be, what the multiplicity would be, and whether that means it crosses or bounces. So this first one, if I set that equal to 0, if I set x plus 7 equal to 0, I get negative 7. You look at the exponent, that's how many times it repeats itself. It repeats itself twice. So that's this definition, the number of times it occurs. Having this means it occurs twice. So its multiplicity would be 2. And since 2 is an even number, if I were to look at this graph, that means it bounces. Okay, so that's the first one. Next one, next factor is 2x plus 1. If I set that equal to 0, I would subtract the 1 and then divide by 2. So I get a fraction there. Anytime I have a number here, I'm usually going to get a fraction. So negative 1/2. It only appears once. There's no exponent. So its multiplicity is just 1. And because 1 is odd, that means if I were to graph it, it would cross right through at that point. Last one is this third factor, the x minus 4. If I set that equal to 0, I get 4. You can see it appears 3 times, so that is the multiplicity. And because the multiplicity is odd, 3 is an odd number, it crosses at that 0. Okay, and if we were to look at the graph, you could see all of those things happening. All right, let's look at another one like this. This one we've got to factor down first. So factoring means starting with the GCF. If you look at all 3 of these pieces, there's an x squared that I can take out. So I'm going to factor out an x squared. That leaves me with x squared minus 2x minus 8. And then just like numbers 3 and 4, I can factor the rest of it down even more. So the x squared stays. And this is just my traditional factoring. So I do x times x. These missing pieces are supposed to multiply to a negative 8 and add to a negative 2. So that would be a negative 4 and a positive 2. So now it's in its factored form, just like this one started out. So now I can write down my pieces. So if I set this equal to 0, my factor is technically just an x. So if I set x equal to 0, I just get 0. And the squared means it's really x times x, so it appears twice. That's its multiplicity. And when the multiplicity is even, the graph will bounce at that point, just like this one did up here. Next, if I set x minus 4 equal to 0, I get 4. There's only one of them. It's not repeating. And so if there's only one of them, that means it crosses. And final factor, x plus 2, if I set that equal to 0, I get negative 2. There's only one of them, that's the multiplicity. And because the multiplicity is odd, it crosses, just like that last one. So let me show you this graph, just so you can actually get a visual. So I'm going to graph this one. We've got x to the 4th minus 2x to the 3rd minus 8x squared. So you can see if we zoom out a little bit. So I have an x-intercept at 0, that's right there. You can see it bounces. Then I have one at 4. This is 1, 2, 3, 4. You can see it crosses right through. And I have another one at negative 2, negative 1, negative 2. And you can see that one crosses right through as well. So just kind of confirming what that table shows me. All right, number 8, we're going in the opposite direction. This one has a 0 at negative 6 with a multiplicity of 2 and a 0 of 2 with multiplicity 1. So starting, write a polynomial function. So we got to start with this. A 0 at -6. So -6, like -2 came from this guy right here. So -6 means there would be an x plus 6. And then it has multiplicity 2, which means it's going to repeat itself. I'm going to have to write this out anyway, so I might as well write it now. And then 2, so like 4 came from this. So if I have 2, it would be x minus 2. And multiplicity 1 means I just have one of them. So write it in standard form means I need to FOIL it all out. That's why I wrote this in its expanded form, since I'm going to have to FOIL it anyway. So I have 2 copies of the x plus 6. I'm going to FOIL this out first. So I have f of x equals, FOIL x times x gives me x squared. Outside gives me a 6x. Inside gives me a 6x. So 6x plus 6x is 12x. And last, 6 times 6 is 36. So that's my first 2, and then I have to FOIL it with my last one as well. So we did this at the very beginning of the unit, this kind of expanded version of FOILing. So I start with the x squared and distribute that here. So when I distribute an x squared, I get x cubed minus 2x squared. Then I move to the 12x and distribute that here. So when I distribute a 12x, I get 12x squared minus 24x. Then I move to the 36 and distribute that. So I get 36x minus 72. So all that's left to do, write it in standard form, means I need to combine all my like terms. So my x cubed, I just have the 1 out front. These are my x squareds, -2, positive 12, means 10x squared. My x's, -24 and positive 36, would be a 12x. And then just that one constant, my -72. So that is my polynomial in standard form.